Hey, Tom, let's turn the page here and take a little bit of a deep dive into a story that could, in the future, be pretty important. NIST has announced their selection for quantum safe encryption algorithms. This competition has been running since 2016, and we've been reporting on it here on the Gestalt IT Rundown ever since. The standards body realized that quantum computing could potentially impact some aspects of RSA based public key encryption. The new encryption method that's been selected is called Crystals Kyber, as well as digital signature methods named Crystals Dilithium, Falcon, and Sphinx Plus. And all of them are designed to be implemented in the coming years for highly sensitive data that could theoretically come under attack from an advanced threat from a quantum computer, as well as the inevitable future of computing development. Tom, are we all going to have to get new tokens?
Well, it depends. Which is obviously the IT answer. And part of the reason why is because the impact of what we can do with a quantum computer on traditional encryption algorithms is still very kind of unknown at this point. And we talked a little bit about some of this back in 2020. I had just recorded an episode talking about quantum computing and quantum safe encryption. And effectively, the Cliff's Notes version is the reason why modern encryption algorithms work so well is because effectively they're doing math problems that take so long to solve that by the time you solve the problem, the data is useless. And we're talking about factoring large prime numbers and using the results of the math operations to create a key that's used to encrypt data, right? Sounds pretty simple in theory, although the math behind it's actually really hard. Well, it turns out that with a quantum computer, with a sufficiently powerful enough quantum computer, you can create an operation that will effectively solve all possible factors for a number in a very short amount of time. And when I say a very short amount of time, I'm still talking about hours or days as opposed to years or eons. And so that's what people are worried about, because with a powerful enough quantum computer with enough data, you can effectively crack encryption in virtual real time in a matter of hours or days. And that's what have people worried. Now, all the way back in 2015 and 2016, the US government said, we've got to fix this problem before it actually causes us to lose all of our data. Because, like AI, once the genie's out of the bottle, you can't put it back in. Now all of the encryption is invalidated. And if you're asking yourself, well, doesn't this sound an awful lot like Sneakers, that movie that they made in 93? Yeah, Alderman, the A in RSA, was a technical advisor on that movie. So the stuff that they did, while farcical, is actually mathematically accurate, just way early, because it's been 30 years and we still haven't built one of these computers. But it's important that we have these algorithms now, because it means we can start implementing them so that when the inevitable comes, we don't have to worry about re-encrypting a whole bunch of old data or changing out a whole bunch of old security signature algorithms, because that's going to be a massive undertaking. Think Y2K, but secretive. Now, Stephen, you dug into some of the technical details on this, and I'm kind of curious to see kind of what you came up with.
Yeah. And let's sort of reduce this a little bit, I think, to help understand what's going on here. I think it's important, number one, to point out that quantum computers currently actually don't do this. They theoretically could, and that's the important part. There's an algorithm called Shor's algorithm that would theoretically allow quantum computers to do some things that are currently really hard and time consuming extremely quickly. And I think that that's the real risk, is that at some point in the future, quantum computers could be developed that could attack the mathematical problems that underlie what's called the trapdoor function of a encryption algorithm. So here's the thing. As you can imagine, if we use the metaphor of like a door lock, if you have the key, it's easy to open the lock because the lock is made for the key. It's kind of the same with encryption. The lock is made for the key in that we know which primes we used, so we can use that in order to solve the problem quickly. The reason we do this, and the reason that we have these challenging mathematical problems built into cryptography, is because of time. Essentially, what you want is you want to make it take long enough, as you mentioned, Tom, to try all the keys, that you can't practically try all the keys, because otherwise you could, right? I mean, you could either build a giant rainbow table or have a bazillion core computer, or frankly, a quantum computer with Shor's algorithm hitting every key at once. And if you can do that, if you can go through all the keys, well, then of course you can open all the doors, because essentially, I mean, imagine if you're that guy in the movie, right? Except your key that you stick in there is literally every possible key, and you turn it, and of course one of them works. That's basically what Shor's algorithm says is theoretically possible with quantum computers. Because the keys that we're talking about are basically solving three hard mathematical problems. You've got integer factorization, you've got discrete logarithms, and you've got elliptic curve discrete logarithms. And all of these things are things that are extremely difficult and time consuming for regular computers to do. So effectively, having these be the problems that underlie cryptography means that with all conventional computers, it's going to take so long that, as you say, it's just not practical to try to guess the key. But with quantum, theoretically, you could guess all the keys at once, or at least something along that lines, and solve the problem in a reasonable amount of time, which means suddenly cryptography doesn't work anymore. So the key here, what's really going on here, is that we've got this new algorithm that's going to replace the trapdoor function. And that new algorithm is based on a concept called learning with errors, which sounds comedic, doesn't it? But essentially, it's a machine learning challenge. And as you may know, machine learning is all about matrix math, and essentially going through and calculating all the answers to, given a whole bunch of different variables, you count all the answers, and then you kind of build on that and build on that. Well, without getting too far into it, because frankly, I don't understand it all that well, but I've tried. And essentially, this whole concept of learning with errors is something that requires you to go through all these iterations. And a quantum computer just can't shortcut. It can't try all the problems because they build on each other. And because of that, theoretically, Kyber and crystals and all that, it might be, it probably is, quantum resistant. But I think there's a couple things that people need to keep in mind here. As I said, number one, this is all theoretical because no quantum computer can do this that we know of at this point. Number two, um, the math says that quantum computers probably won't be able to do this. But of course, we don't really know that either because we kind of don't have them. I mean, it's all theoretical. And then number three, everybody's immediately going to jump to, oh, the NSA has compromised NIST, and this is blah, 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 and there's secret backdoors and all that kind of stuff. And you know what? We can't guarantee that there aren't. Hopefully, there aren't. But it's entirely possible that all of this is a complex ruse or a good excuse for NIST to compromise encryption again, which they did before, and that's one reason that everybody's really frustrated. But the problem is there's nobody other than NIST that can set cryptographic standards, and so kind of we all in the world kind of have to trust them anyway. I don't know if you've got anything more to say about that aspect, Tom.
Well, actually, I do, because there's a couple of other things you have to keep in mind. So, Stephen, you're absolutely right that that we're working on a theoretical basis right now. You have to have a super powerful quantum computer in order to do this. To give you an idea, the most powerful quantum computers in existence right now are running a little bit over 100 qubits. You don't need to know what a qubit is. Actually, if you do want to know what a qubit is, we'll link an article. We'll link the conversation that I had about this. But effectively, think of a qubit like a gigahertz on a processor. So right now, the most powerful quantum computers are running at a few hundred qubits, like 120. IBM and Google think they can get to a 5,000 qubit computer maybe by the end of next year. You would need a computer in the several millions of qubits in order to be able to decode this stuff in a matter of hours. And that doesn't take into account error correction. It's not just that you have all the gas, you actually need a little bit of brakes. Because with the way that this whole thing works, which again is way too complicated to talk about here, it's not just going fast, it's being able to correct all the errors that you create along the way to be able to figure out all the possible states of the qubit. And we're still not really doing the error correction part right now. We're building really, really fast computers, but they're effectively producing white noise right now. So that's one of the reasons why we're probably thinking that this is going to be a big challenge to solve, is because you not only have to have superpower, but you have to be able to read the results in order to make them make sense. The other thing that I thought was really interesting from this was they interviewed Bruce Schneier, who's a very well known security researcher, and they asked him about why it took so long for this process to come back. And Bruce effectively said that there were 96 algorithms that were submitted for encryption and digital signatures when the first round was opened up, and they hammered these things. They weren't just testing to see if they were going to be resistant to quantum interference effectively. They were testing them to make sure that they couldn't be accidentally compromised for a whole lot of other reasons. And it's funny because in the last round, there was actually an algorithm called Rainbow that was very popular. And when NIST and their team got a hold of it, they absolutely destroyed Rainbow to the point where not only was it not quantum resistant, it could have actually been compromised by a modern laptop. There was like some kind of factoring thing that was built into it that effectively allowed people to just shortcut right through it. And in the complete honest transparency, dilithium and Kyber had a similar problem, but not to the degree that Rainbow did, and they were actually able to patch that out so that they were able to select those as the final things. And to talk about the NSA point, yes, now that we know that the NSA has actually been kind of monkeying around with elliptical curve technology, and we've actually had a number of stories about that here on the rundown. Someone actually interviewed somebody from the NSA a couple of months ago, right when this the announcement was made that they had finalized it and they were going to make the announcement soon. And someone went to the NSA and was like, "Hey, are you guys monkeying around with this again?" And cross my heart and hope to die, the NSA says that they didn't do anything this time. Now, I will say that given the amount of testing that these things went through from researchers in the community as opposed to government researchers, I would tend to err on the side of probably this being something that is at least somewhat protected. I hope that I don't have egg on my face in a couple of years when it comes out that it actually wasn't. But the other good thing is that now that we have a baseline to work from, we can actually start developing more amazing, crystal named algorithms like, I don't know, like Mcron or something. But basically, now that we know where we need to go to get this solved, we can start building on what we have as opposed to just hoping that this is going to be enough. Because if you believe that, remember that at one point that we believed that DES was uncrackable. And well, now we're here today where we know absolutely that it totally is.